So, in case of multiple degrees of freedom, actually we want to check how many possible types of degrees of freedom are linked with that system. So, first of all we need to understand what is meant by the degrees of freedom. It is defined as the number of masses multiplied by the possible type of motion each mass can withstand. So, here in this case we can consider that there are two possible masses m1 and m2, and possible type of motion is only translational or x direction only. So, we will multiply by 2 with 1 and degrees of freedom of the system are 2. So, consider here another example, that is of the pendulum case. So, here in this case what you people can say, how many possible type of masses are there? Yes, please. Number of masses?
Two masses, sir.
Two masses. And possible type of motion by each mass?
So one, sir.
Yes, rotational motion only. So it is 1. So you can say 2 multiplied by 1, that is 2. That means this system can withstand 2 degrees of freedom motion. Okay. In this case again we will have 2 degrees of freedom. So does stiffness element will affect the degrees of freedom? Anyone? If we have 2 springs or 3 springs connected or 4? Yes, please. Anyone? Because in the main formula there is no effect of the stiffness element on degrees of freedom. So, for finding the number of degrees of freedom, only number of masses and possible type of motion with each mass is required. So, see in this case we have 2, 3, 4, 5, 6 masses. Possible type of motion is 1. So, we have 6 degrees of freedom here. And this is the time response of the whole system. Okay. Now, question is why we need to study the multiple degrees of freedom system? Because in case of single degree of freedom system, we have solved certain cases for the undamped cases and damped cases as well. So, we had only one equation of motion for a single degrees of freedom, and there was a one nature frequency also for that system, and there was only one possible type of mode shape as well. In case of multiple degrees of freedom, so degrees of freedom will decide how many possible type of equation of motion our system will be carrying. So, for example, in this case degrees of freedom are 2. That means this system will be only solved with, it is only possible to solve this kind of system with how many type of equation of motion? Number of equation of motion required to solve the system? Yes. Anyone?
Sir, 2, sir.
Yes, 2. Keep in your mind that number of degrees of freedom will decide number of equation of motion of that system, number of nature frequencies of that system, number of resonant frequencies of that system, number of mode shapes of that system, and all of them will be equal. For example, if we have 2 degree of freedom system, if we have 3 degrees of freedom system, so I am considering the example of 3 degrees of freedom system. This system will have 3 possible type of equation of motion. This system will have 3 nature frequencies. This system will have 3 mode shapes. Okay. So, this is what it is expected how to solve the complex systems, because complex system consists of various masses and various possible type of motions are linked with them. So, we need to solve the whole system, and also the mass of maybe the mode shape of one component of the system will be affecting the mode shape of other as well. So it depends upon the excitation frequency which mode shape it is approaching. For example, if we have a 3 degrees of freedom of system, then what will happen? There will be 3 possible type of mode shapes that a system can withstand. Now each possible mode will excite at a particular excitation frequency. When that excitation frequency, because there will be 3 natural frequencies of that system, okay, and if system is vibrating at natural frequency in such a way that excitation frequency is approaching first natural frequency, then system will excite at first mode shape. If excitation frequency is approaching second natural frequency, then system will vibrate at second mode shape. If system is excited at third natural frequency, then it will try to vibrate at third mode shape. In complex cases, there may be cases where system will be vibrating at multiple mode shapes and it is very difficult to understand the system. Okay. So normally if system is complex, then it is very difficult to solve it analytically. So we perform its simulation on ANSYS. In case of ANSYS, we have a model analysis toolbox in which we can easily draw the complex system, and we will provide the initial conditions to that system. So after providing the initial conditions and providing the possible meshing properties, we can understand the possible type of mode shapes. So for example, in case of a crankshaft, so you people will be considering, sir, what will be the degrees of freedom of a crankshaft that is provided within the IC engine. So it depends upon the shape of geometry and possible type of motion again. So most of the people are working on that. They need to draw the its model first of all, and they will import it in the model analysis, and then they will provide the initial conditions, and after that we will check how many possible type of natural frequencies are associated with that. But keep in your mind, we are sometimes interested to find out the first natural frequency for most of the complex cases. Why only first natural frequency? Although we are interested to solve all the natural frequencies and all the mode shapes, it is okay, but sometimes we need to find first natural frequency only. Why? I will provide its answer in coming 2-3 lectures. Why we people are always interested to find out the first natural frequency. Although we find all the natural frequencies, but we consider that first mode shape is very important. Why it is so? We will solve it in coming lectures. Okay. So I will need.
सर इस तरह हो सकता है
Yes. Sorry.
सर एक सिस्टम हो, दो मासेस हो सर एक सिस्टम में, लेकिन एक का 1 डिग्री ऑफ फ्रीडम हो तो दूसरे का 2 डिग्री ऑफ फ्रीडम हो.
Okay, I am understanding. Look here, please. In case of earthquake, you people know that if we have a tall building of about 15 to 16 floors, you are talking that case. Okay, one of the example. So in that case, we have a multiple degrees of freedom. Why? Because we have a multiple masses. Okay, because each floor will be considered as a mass, and columns will be providing a stiffness element. If you have a room, then you can consider that walls are a stiffness element and roof is your mass. Are you getting my point? So if you have a two story home, then you can consider you have a two masses, and walls are providing the stiffness element, and possible type of motion you have to consider. For example, it can move in x and y direction, translational motion, rotational motion. So after that you will multiply and you can find the possible type of degrees of freedom. So point is that it is very difficult to find to solve such systems analytically. Please look here. Vibration mode shapes of a tall building. So what I want to show you people, this is the complete response of the tall building. Okay, this is your complete response of tall building. It consists of about 48, 49, 50 floors. Okay, and you can see this is the first natural frequency and first mode shape will be like that. Observe its motion first. Only this one. This is the response of only first mode. If building will be excited at second mode, then its response will be like that. If it is excited at third mode, its response will be like that. Now it depends upon the possible type of excitation force which mode is exciting. You can see that first mode is such that your free end is at maximum displacement. Okay, it behaves like a cantilever beam. So this end will be your node, this end will be your antinode. Now consider this case. If you will draw a waveform, then its response will be like that. That means this system have two nodes. This is one node. You can see here displacement is 0. This is your second node where displacement is 0. And where we have maximum displacement? We have maximum displacement here and free end. Okay. Now consider the third node. In case of a third mode, we have how many nodes and antinodes? For example, this is your one node where displacement is 0. Where is displacement 0? Another point. It is about that point.
सर बेस पे था
यस बेस तो है ही है ना, बेस तो नोड है, लेकिन बेस के अलावा भी एक पॉइंट है जो नोड है, ये पॉइंट है. ठीक है. और कौन सा पॉइंट है? यहाँ पे आपका डिस्प्लेसमेंट 0 आ रहा है. बहरहाल ये दो नोड्स आपको नज़र आ गए. इसी तरह दो इसके एंटी नोड्स भी होंगे. एक ये एंटी नोड है इसका, और इसी तरह जो है वो एक यहाँ पे एंटी नोड बन रहा है, एक यहाँ पे बन रहा है. तो आई थिंक सो एक नोड आपका यहाँ पे होगा. 3 नोड्स होंगे और इसी तरह 2 इसके एंटी नोड्स होंगे. एनीहाउ, सो अगर मल्टीपल मोड्स पे आपकी बिल्डिंग एक्साइट होगी तो उसकी जो वाइब्रेशन बिहेवियर होगा वो कुछ इस तरह का होगा जो एक्चुअल अर्थक्वेक में हो रहा होता है. बिकॉज वो कॉम्प्लेक्स सिस्टम होता है आपका, और कॉम्प्लेक्स मल्टीपल डिग्रीज ऑफ फ्रीडम से वो वाइब्रेट कर रहा होता है. आर यू गेटिंग माई पॉइंट?
Yes, sir.
Now case is that every mode have a particular excitation frequency and possible type of orientation, and also a possible type of amplitude as well. It may be possible there will be a small amplitude with first mode and there will be a large amplitude associated with the third mode. Okay, so it depends upon the excited mode. Okay, are you getting my point? Why we need to study the multiple degrees of freedom? So
Yes,
if
sir.
if it was a single degrees of freedom, then how we can find the natural frequency? Already we have solved the numerical, where we have a mass at the top and mass and base will be connected by a stiffness element. That just like the case of the water tank, we have solved in sessional 1. You remember that case? What was the natural frequency of the water
yes sir,
tank?
उसमें वो
Yes.
यस सर, उससे इक्वेशन डिफ्लेक्शन ऑफ द इक्वेशन से आता था सर, वो
यस बिल्कुल, वो से आपने वो
उसको
कैलकुलेट किया
सॉल्व
था।
करके।
तो इसी तरह जो है ना, अगर आपके पास सिंगल डिग्री ऑफ फ्रीडम मैथ फ्रीडम सिस्टम है तो उसका कैसे आप फाइंड करते हैं नेचुरल फ्रिक्वेंसी? एफ एन इक्वल्स 1/2 ओके,
यस सर,
बट
केवल
yes,
यस
it will be first mode. But what about the other natural frequencies? How we can find the other natural frequencies? So in order to find that natural frequencies, we need to solve the system for multiple degrees of freedom. We are always interested to find all the possible kind of excitation frequencies. For example, if we have a flexible rotor, then it will have a multiple mode shapes and it will have a multiple equation of motion and multiple natural frequencies. So we have to consider all the possible kind of critical frequencies that are possible for that kind of flexible rotor. Okay. Now consider this example. So this is your building structure 1, 2, 3. So 3 stages are here, 3 stage building is here. So top of each floor is considered mass. This is your mass second floor, this is your mass of third floor, and these are columns that are considered stiffness element. So this is your scaled down model of a 3 stage building. Let's consider its motion. Please pay your attention. This is the shaker. We are providing a particular natural frequency. Vibration is starting at very lowest frequency, and we will see that a time will come when this system will excite at the lowest natural frequency. Then a time will come, it will come out of that mode shape, and then excitation frequency will try to approach a second mode shape, and after that it will come out of that mode shape, and then system will try to excite at a third mode shape. Please pay your attention. Each mode will excite at a particular excitation frequency that will be approaching its natural frequency. So this is your first mode shape. You can see that is occurring at 4.35 Hz. As I have shown you people in the previous video, where you can see that first mode was such that its cantilever beam free edge is always at maximum displacement. So this is your first mode shape that is occurring at 4.35 Hz. Okay. You can see that base motion is increasing its excitation frequency continuously. Okay, this frequency is increasing continuously. So you can see that when the system is now away from 4.35 Hz, for example, its frequency is now about 6 to 7 Hz, then its vibration is decreasing. Why? Because why system excite at its mode shape? Anyone? Because it is a point where excitation frequency approaches natural frequency of body. It may be its first, second or third natural frequency or so on. It is regarded as the first critical frequency, second critical frequency, third critical frequency. Okay. Now it depends upon the nature of the critical frequency, that if system is excited at a critical natural frequency, then if we are adding small amount of energy within the system, then it will be providing a great response at that critical frequency. If system is moving away from critical frequency, what will happen? If we will be providing energy within the system, then it will not be exciting like as the case of the critical case. In critical case, excitation will be more. Only small amount of excitation force is enough to excite the system at large amplitude at critical modes. Are you getting my point?
यस सर। सर एक टाइम पे एक ही उससे फ्रीक्वेंसी के साथ वो होंगे
Now,
कहते
now,
हैं।
yes, very good question. Very good question. It depends upon the mode shapes. So that's why we need to find out the mode shapes. Reason is that it may be possible that multiple floors will have the same natural frequency, and they will be vibrating at the same mode shape. But consider that at one excitation frequency, if system is excited only at one excitation frequency, it will be vibrating only at that particular frequency. Okay. Now, if that particular frequency is matching what type of mode shape of that building, it will be vibrating at that mode shape. If I am exciting the system at multiple mode shape, at multiple excitation frequencies, for example, this is one shaker, also I am going to attach another shaker here. Now, what will happen? There are two excitation forces. Okay. If we have two excitation forces, now there will be, now what will happen? There will be multiple mode shapes of a building vibration, because we have a multiple excitation forces, and it may possible that this excitation force is providing one mode and this excitation force is providing a second mode, and both will add up and your response will be very complex. Okay, please move on. So this is your second mode. You can see at second mode, this is your node and this is also your node. This is your ND node and this point is your ND node. There is maximum displacement at ND node and there is zero displacement at node. जब आप बिहेवियर को चेक कर लेते हैं मोड शेप की, अगर आप मोड शेप देख लें तो आप ये भी बता सकते हैं ये किस मोड पे वाइब्रेट कर रहा होगा. फर्स्ट मोड शेप पे आपके पास वन नोड था और वन ही एंटी नोड था आपके पास. इस केस में आप देख सकते हैं आपके पास टू नोड्स हैं. प्लीज़ ऑब्जर्व. Now consider that second mode is excited at 12.55 hertz. Okay, so this is your second critical frequency for your system. So why we need to find all the critical frequencies? Because if sometime, for example, if your steam turbine is running at about 10,000 rpm to 30,000 rpm, this is your operating range of a steam turbine. So we find critical, all the possible kind of critical frequencies of a steam turbine rotor and all the possible type of mode shapes. Why we find mode shapes? Mode shapes help us to find out at what excitation frequency system will excite, and against that excitation frequency we can calculate the rpm. So we can say that we can find the possible type of rpm where system will excite. So we will provide within the catalog that this steam turbine rotor should not run at these possible rpms. For example, I will say please do not run your system at 12,000 rpm, 18,000 rpm and 24,000 rpm. Other than these rpms you can run your system. Normally we people consider that if your system is 1/3 away from a natural frequency, if your system is excited at 1/3 away from natural frequency of the system, then it is in the safe zone. It is in the safe zone. Okay. Okay, so in this case, you people have seen the possible type of mode shape that this system can withstand. About they people have provided above 30 hertz excitation frequency, and within 30 hertz, two modes are occurring there. Now it may be possible that in next 30 hertz, that means from 0 to 60 hertz, maybe this body will have third mode shape as well. So it depends upon our nature of interest, that sometime we are interested to find under what range of frequency first mode is occurring, under what range of frequency second mode is occurring, and under what range of frequency third mode is occurring. This is your
A 1 degree of freedom
Third
mass
case.
spring system has one natural frequency and one vibrational mode shape. The mass oscillates back and forth, or in this case up and down, at a frequency that depends on the inertia or mass and elastic or stiffness properties of the system.
okay. So what is this? This is your first mode.
A 2 degree of freedom mass spring system has two natural frequencies and two mode shapes. In the first mode shape, first frequency, the two masses move in the same direction at the same time.
So you can say that in case of 3 degrees of freedom, what will happen? There will be 3 possible type of mode shapes. Now what are the possible type of mode shapes? How system will vibrate? We are interested to find that. Please, anyone who will tell me why we need to find the mode shapes? जो बताएंगे उनको 5 मार्क्स एक्स्ट्रा दूंगा एग्जाम में. Yes. Anyone? Why do we need to find the mode shape? Anyone? Okay, so let me explain. For example, if system is excited at first mode, then we people can see that nodes are here and here. Sorry, antinodes are here and here, nodes are here and here. So we people can see maximum displacement is at this point and this point. Okay, in second mode we people can see there are three nodes and two antinodes. This is your first node, second node, and third node. So these are your antinodes. Now according to the analytical description, we people have observed that if we people are going to avoid maximum amplitude of a particular mode, then we need to provide a support or a stiffness element at antinode shape only. Okay. For example, if we are going to provide some support or some kind of support or some kind of stiffness element, if I will provide it at node, then it will have no effect. अगर मैं ये पाइप लाइन है जो वाइब्रेट कर रही है आपकी, और अगर मैं सपोर्ट जो है वो नोड्स पे लगा देता हूँ, तो वाइब्रेशन पे कोई वाइब्रेशन एम्पलीट्यूड पे कोई इफेक्ट नहीं आएगा. लेकिन अगर वही सपोर्ट मैं इस पॉइंट पे लगा दूँ एंटी नोड पे और इस एंटी नोड पे लगा दूँ, तो इट मे बी पॉसिबल दैट 90% ऑफ वाइब्रेशन एम्पलीट्यूड विल बी reduced. So there are certain kind of ways where we can decrease the vibration amplitude of a particular mode. For example, we can either provide a particle stiffness element at a particular point. We may provide a damping element within the system at a particular point. So in order to decide where to add a support within the structure, we need to find the mode shape, and to find the mode shape we need to find the natural frequencies, and to find the natural frequencies we need to solve the analytical model, or we need to draw that system in the simulation system and solve it in the simulation environment. So you people know that here we have two masses and one possible type of motion. So this system will have 2 degrees of freedom and two possible type of natural frequencies and two mode shapes. Agreed? Now what will be the possible type of mode shape? One possible type of motion is that both masses will be moving in same direction. Okay, if both masses are moving in same direction, what does this mean? They will be on the, if I will draw mean line from node to node, so I am drawing the mean line here, and now I have to draw the first mode shape. First mode shape is saying that both masses will move in the same direction. So here you can see both masses are at same direction, for example on the same side of the mean line. Okay, so for example if this mass is at maximum displacement of 5 meter per second, 5 meter, and this mass is at a displacement of 5 meter as well, so I will draw a maximum displacement of 5 meter and 5 meter, and this is your possible type of mode shape. Now it may be possible that if this mass is displaced 5 meter, then this mass will displace 2 meter. Then what will happen? I will draw first point 5 meter here and 2 meter will be about here. So I will connect this node here with this antinode and this node here with this antinode, that will be about here, and then I will draw this line here. So this will be a possible type of mode. And what will be the second possible type of mode? Both masses will be moving in opposite direction. What does this mean? One mass will be on the one side of a mean line and other will be on the other side of mean line. So you can see the possible type of motion will be here. Amplitude of these masses will be defined by the analytical model. For example, what possible kind of amplitude the masses will be carrying. We will in case of analytical models, we will solve 2 degrees of freedom system and 3 degrees of freedom system for mass spring system, compound pendulum, coupled pendulum and torsional vibration case. So we will find out multiple equation of motions, multiple natural frequencies and multiple mode shapes. I will let you people know how to draw the mode shapes analytically. Okay, for example, for mode shape, for first thing we should know is that what is the natural frequency. Second thing we people have to know is that what possible kind of amplitude a possible mass is carrying with. For example, what is the possible type of amplitude of the mass 1 and mass 2, and after that we can easily draw the mode shape. Okay, move on.
Shapes. In the first mode shape, first frequency, the two masses move in the same direction at the same time, basically looking like a 1 degree of freedom oscillator.
So in case of the first mode shape, you people can see that both masses are moving in the same direction at the same time. Okay, it is also behaving like a single degree of freedom system. These are your exciters.
In the
Excitation is
second
word from
mode
midpoint.
of vibration, the two masses oscillate in opposite directions, one going up while the other one's going down. At the very center in between the two masses is a node, a
This is
point
your
that
node
doesn't
point.
move at all.
This is also your node point. This is also your node point. These 2 points are going and creating
A
antinodes.
3 degree of freedom mass spring system has 3 natural frequencies and 3 mode shapes. In the first
Okay, you can see here we have a 3 masses. So here we will have a 3 degrees of freedom. So we will see in first degrees of freedom all masses will move in the same direction. In second degree of freedom we people will have a 3 nodes and 2 antinodes. Okay, and in third degrees of freedom we people have 4 nodes and 3 antinodes. Okay, so when you people will solve these systems, multiple degrees of freedom systems, then you people will understand this topic very perfectly. I am just showing you people with possible type of videos in order to understand your conceptual expectation about the multiple degrees of freedom. Why we need to study the multiple degrees of freedom? Because complex cases always have a multiple degrees. Okay, are you people getting my point?
Yes, sir.
Yes, sir.
First mode shape, all three masses move in the same direction at the same time, with the center mass moving slightly farther than the outer two. In the second natural mode, the center mass is stationary at a node point, while the two outside masses move with opposite phase in opposite directions.
So you can see here we have three nodes. This is first node, this is second node, and this is third node. Now this mass is acting like a node.
In the third natural mode shape for the 3-degree freedom system, all three masses alternate in directions or phase. The two outside masses move together, and the inside middle mass moves in the opposite
First
direction
node,
compared to the outer
second
two.
node, third node is here, and fourth node is here, and three antinodes.
Hopefully by now you'd be able to guess that a 4-degree freedom system would have 4 natural frequencies. In the first mode, all 4 masses move together. The outside.
Okay, so how many nodes in will be 4 degrees of freedom? Anyone? Anyone? How many possible type of nodes will be there and antinodes will be there? Yes.
5.
Very good. 5 nodes and
4 antinodes.
4 antinodes. And possible type of mode shapes will be? How many type of mode shapes will be there in 4 degree of freedom?
Sir, 4.
Yes, 4. And how many equations are needed to solve the system? Equation of motion?
Sir, 3 चाहिए होंगे.
No, 4. Please
Sir,
try
sir.
to understand. I have said that all of these things are equal. Number of degrees
so
of
for-
freedom is equal to number of equation of motion is equal to number of natural frequency equals number of resonant frequencies equal number of critical frequencies equal number of mode shapes. Okay? जितने मैसेज होंगे या जितने डिग्रीज ऑफ फ्रीडम होंगे उतनी ही इक्वेशन चाहिए होंगे हमें उसको सॉल्व करने के लिए एनालिटिकली.
2 slightly less amplitude than the 2 in the center, but the entire system moves in the same direction at the same time. In the second natural mode, there's a node at the very center of the system, and the two halves of the system, the right half and the left half, move in opposite directions. In the third mode shape, the inner two masses move in the same direction at the same time, and the outer two masses move in the same direction at the same time, but opposite the inner pair. In the fourth mode shape, every other mass oscillates at a different direction. There are 3 nodes, one between every pair of masses.
Okay, so we will solve all of these systems analytically. How we can find the possible mode shape? For example, if this body is vibrating at fourth node in this way, then how they have come to this shape? We people will check how this body is vibrating at fourth node in this way. Okay, so we will find out the possible type of amplitudes that each mass can carry, and we will connect them with the antinode, and finally we will have the possible type of mode shape. If system have 4 masses, then there will be 4 mode shapes, and we will check what will be the first mode, what will be the second mode, what will be the third mode and fourth mode. But it is quite difficult to solve 4 degrees of freedom. It will take, not difficult to solve, but it will take very much time. So normally we prefer to solve 2 or maximum 3 degrees of freedom in our classes, and in case of paper also we provide 2 degree of freedom or 3 degree of freedom problem as well. Okay. Okay, now this was all about practical explanation how we can excite the system that have multiple masses or multiple stretches, and how we can find the complex mode shapes. Okay. Now, if we will go for the complex bodies, for example, in case of aeroplane wing, in case of aircraft wing, what you people say, how we can find the mode shapes? Because in case of the aeroplane wing, you people will be interested, sir, how we can find the mode shapes. There are two possible ways. One is we can solve analytical model and drive the mode shapes. Second way is to solve the system in the simulation environment, and third way is to solve the system in the experimental environment. So, analytically we will solve possible type of problems. In case of simulation, as we are doing the ANSYS lab as well. So, I will show you people how aircraft wing vibrate at certain modes, and what is the possible natural frequency at which a particular mode is exciting, and how we can find the multiple mode shapes using ANSYS as well. Okay. So, two domains are covered in our one domain will be covered in the mechanical vibration class, that is analytical problem. Another domain will be covered in the ANSYS class, that will be your DME lab, and third way is to solve the mode shape in the laboratory environment or by experimentation. How we can do that? We need a scaled down model of aircraft wing, and we need a exciter as well, harmonic exciter. So, what will happen? We will connect multiple vibration transducers at multiple places of the aircraft wing. As you people remember, in the previous lectures, we people have shown, we people have seen industrial case of oil and gas pipeline, where there were the multiple nodes that were calculated for the particular type of pipeline. There was a problem within the reciprocating compressor, and that vibration was traveling across the pipeline, and then we have solved that problem by considering the mode shapes. And in that example, we have also found out the wavelength. So, wavelength will let us know where to connect the vibration transducers. So, let's see that video. So, this is the scaled down model, and they are connecting the vibration transducers at certain wavelength. This certain wavelength is calculated by the certain analytical formulas, and harmonic exciter will provide the excitation frequency.
Ground vibration
This excitation
test. We
frequency
have the
will be
aircraft suspended
approaching
on a
actual
bungee system to
excitation
simulate
frequency.
a
Keep in your mind, this excitation frequency will be like that of the excitation frequency of air, that a aircraft wing can withstand within the air environment or actual environment. So, this is only possible way that we will know what possible type of modes this aircraft wing can withstand, and then we can make our design more reliable and stiffer.
free flight environment for when we actually excite the vehicle. How we excite the aircraft
This
is
is your
through some
harmonic exciter.
magnetic shakers. We have one on each
Our
wing
shaker.
tip and a vertical and also a 45-degree skewed angle. And with that excitation, we have various sensors all over the aircraft where we're measuring the response on these accelerometers. We don't need to put in too much force whatsoever. It's a really small shake that we put in that's good enough to get all the structural frequencies and mode
These
shapes
are
out of the
vibration
article that we
transducers.
need. We're also
How vibration transducers work, I have already explained in the vibration isolation, and also we have solved one of the numerical problem on vibration transducers, how to find the natural frequency of vibration transducer and so on. Please do not forget to watch the lecture.
gathering data with a photogrammetry system and a fiber optic or FOSS system. These other external systems, we have to excite the aircraft a little bit more and use a higher force level. Okay, flight accels. Record. 5, 4, 3, 2, 1.
Now it is exciting, and here you can see that multiple parts are exciting at a multiple modes. Every part have a certain mode as a mode of excitation, and we are capturing the motion using vibration transducer in a time domain signal. Here you can see this is a time domain signal.
Shaker stopped. Using this data, we can get the mode shapes and the flexibility out of the aircraft that it has for its structural frequency.
So what are mode shapes? They are the motion patterns that are caused by external forces on an aircraft to a particular frequency. Okay.
And use that data and update and validate our finite element models. And once we have our finite element models updated, we use those models to help run our flutter analysis that gives.
So why we are finding the multiple degrees of freedom? Why we are interested to find the mode shapes of a aircraft wing? Because like in the case of the heat exchanges, industrial heat exchanges mostly failed because of the phenomena known as fluid elastic instability, in which inside tubes of heat exchangers collapse. Okay, that phenomena is known as fluid elastic instability. Some kind of in case of the civil structures, there is a phenomena known as fluttering, and in case of the transmission wires, if there is a resonance, then there will be a galloping phenomena that result in the blast of transmission wires. And this is your fluttering analysis. Fluttering analysis is in case of civil structures or aircraft structures. You can see that when excitation frequency will approach a particular mode, then it will excite that mode at a large amplitude. Only small amount of energy that is entering a system at a resonant point will excite a system at a very large amplitude. And what will happen? There will be a fluttering phenomena. What is fluttering? Fluttering analysis predicts instability of an elastic structure in the fluid medium. So it will determine the point where your structure will be in the phenomena of instability. Okay. So fluttering analysis phenomena can be predicted experimentally as well. What are possible type of excitation frequencies where the system will excite? So we make our structure in such a way that if our excitation force of the air or if medium excitation force is in this domain, then our structure should not operate within this domain. So this help us to understand and to avoid the very expensive disasters. So अगर हम ये चीज़ें ना करें और एरोप्लेन आप किसी भी स्पीड पे जो है वो रन कर रहे हैं अपने फ्लूइड मीडियम में, तो किसी भी वक्त किसी भी मोड शेप पे कोई पार्टिकुलर कंपोनेंट उसका कोलैप्स हो सकता है और कोई भी इंसिडेंट जो है वो अकर हो सकता है. उस चीज़ को अवॉइड करने के लिए ये सब कुछ हम करते हैं. सो दिस इज़ योर लास्ट वीडियो, वेरी इंटरेस्टिंग वीडियो, प्लीज़ वॉच इट.
What we have here are two almost identical pendulums. Now you can see that the motions of them are independent. You can see that the motion of one has no effect on the other. It doesn't matter what I do with the other.
So here you can see here we have our two suspended pendulums. These pendulums are not connected to each other. They are uncoupled. Okay, there is no stimulus element in between. So if I will vibrate this pendulum, and if this pendulum is vibrating anywhere, there will be no effect of this pendulum on vibration of second pendulum. Okay,
They're just swinging as though they're completely separate. The word that scientists use is uncoupled pendulums. Now what I've done is I've added a spring joining the two pendulums.
now I have connected a stiffness element here in between the suspended pendulums. Now what will happen? Now it is called coupled pendulum. Most of the complex cases are always coupled. Okay, so there is effect of one body motion on the other. So if I will vibrate this pendulum, then check its effect on this pendulum, how this pendulum is vibrating. So they will vibrating at a particular mode. Maybe at first mode they will be moving in the same direction, and at second mode they will be moving in the opposite direction. So what is the possible type of mode shape for a coupled pendulum? We will also solve this problem analytically in class, inshallah. First seed and experimentally. I am showing you people videos because you people are not solving. I hope that these problems are not solved in your theory of machine lab, and if these problems are not covered, then I think that instead of solving analytical models, first we need to understand the systems, why we are going to solve these systems.
Physicists
How they are-
call this a system of two coupled pendulums. Now let's see what happens to the motion now that there's something joining the two. I'm going to try to move just one of the pendulums and see what happens.
So this video is available online on YouTube. I will also provide the source link.
You'll notice now that the motions of the pendulums are no longer independent. What one pendulum does affects the other. In fact, if you look really closely, you should notice that from time to time, one of the pendulums will stop moving while the other one is moving, and then they'll swap over, the other one stopping while the other one is moving. The reason for this is the conservation of energy principle. The total energy of this system should stay the same, but what happens is that the energy is passing from one pendulum to the other through.
So this is very important point. You people have seen that this pendulum was at the rest position, and he has excited this pendulum. So you can see when this pendulum was excited, then first this pendulum was moving, and then energy was transferred to this pendulum because of a coupled mechanism. When energy was transferred to this pendulum, then the vibration amplitude of this body was decreased. Okay, so it is energy is spread now. Energy of this pendulum is transferred to this pendulum. So this is the working principle of shock absorbers as well, how they behave. We suspend another element in the buildings. So what happen when there is an earthquake, then building vibrate, okay, and then that vibration transferred to the suspended pendulum or shock absorber. It act like a second mesh, and what happen, motion transfer from a first mesh to the second mesh, and energy is dissipated by the second mesh, and first body is coming to rest. So this is how we can control the magnitude of the first mesh, because first mesh is primary mesh, and primary mesh is building, and we do not want that our building structure is excited at a maximum amplitude. So we always want to control its motion amplitude.
The spring. So from time to time you'll have one that's not moving, so it has its energy is zero, while the other one moves, but then it transfers its energy to the other, reversing the situation. Now, because there are two pendulums, it turns out that all those complicated motions you saw before can be broken down into a mixture of two motions that we call modes. The first one is this one here, where the two are.
Okay, now he is displacing both pendulums from the same displacement in the same direction. Now let's observe the possible type of modes.
Swinging exactly the same time in the same way.
Okay, so this is your first mode, where both
And you'll see that they
pendulum
always
are
stay
moving
in
the same
sync.
direction.
Neither of them ever stops. And the other motion,
Other type of excitation motion is that both will be displaced from the same displacement but in opposite direction. Now let's observe the motion.
sometimes called a breathing mode, is when they're moving in opposite directions, like this.
So this is your second mode.
They're still in sync, but always moving in opposite directions. All of the other complicated motions that you saw is just a mixture of these two modes.
Okay. Let me show you people last video, and inshallah after that we will end up our lecture.
सर आपने फाइनल का कोर्स नहीं लिस्ट किया अभी तक?
वो मैं बता देता हूँ उसको।
यार 5 हफ्ते पड़े हुए हैं अभी, चिल करो।
कोर्स पूछने का फायदा क्या है, तो अजीब सा बनता है।
Okay, now this is the scaled down model of a steam turbine flexible rotor. You people can see that why we need to find the mode shapes or critical speed. Always you people have studied about the what is the critical speed of this and so on. So why we need to find out the critical speed. Here you people will see that there are multiple critical speeds at a particular one particular flexible rotor is withstanding. So we need to find out that numbers of our RPMs. How to find out the frequency from RPM? For example, if RPM of a rotor are 10,000 RPM, मुझे फ्रीक्वेंसी बताइए कितनी होगी। अगर 1000 RPM है किसी बॉडी की, तो आप मल्टीप्लाई बाय 2 पाई करें और डिवाइड बाय 60 करें, तो क्या बना?
ओमेगा।
यस, ओमेगा। तो ये जो ओमेगा की वैल्यू आ रही है, ये आपके पास क्या है, रेडियंस पर सेकंड में है फ्रीक्वेंसी की वैल्यू। फिर आप इसे एफ एन भी फाइंड कर सकते हैं। ओके, एफ एन इक्वल्स 1/2 पाई के ओवर एम स्क्वायर रूट। सो दिस इज हाउ यू कैन फाइंड अ नेचुरल फ्रीक्वेंसी फ्रॉम अ particular critical speed. So we need to find that particular RPMs, because we will provide in catalog. Please do not run your flexible rotor in between these range of RPM. अक्सर आप लोगों ने देखा होगा, अगर किसी ने इंटर्नशिप की है, जब स्टीम टर्बाइन को रन किया जाता है, जब स्टॉप किया जाता है, तो एक पर्टिकुलर आरपीएम से ही उसे मूव कर दिया जाता है। वैसे नॉर्मली ये होता है कि जब भी किसी आप बॉडी को, इंजन को स्टार्ट करते हैं, तो बहुत आहिस्ता आहिस्ता वो स्टार्टअप होता है, आरपीएम आहिस्ता आहिस्ता इंक्रीज़ होते हैं। लेकिन हमेशा जब क्रिटिकल स्पीड अप्रोच करती है, तो हम उस पॉइंट से जल्दी से पास थ्रू कर देते हैं अपनी बॉडी को। अगर हम ज़्यादा देर के लिए अपनी बॉडी को रन करेंगे उस पर्टिकुलर आरपीएम पे जहाँ पे क्रिटिकल स्पीड आ रही है, तो क्या होगा, एनर्जी विल बी प्रोवाइडेड एट अ पॉइंट वेयर एक्साइटेशन फोर्स इज अप्रोचिंग नेचर स्पीड, एंड व्हाट विल हैपन that it will excite body at a very large amplitude, even your system can collapse.
Reliability Solutions presents Key Tips, Techniques, Behaviors. Problem in industry today. Some people estimate about a third of your machines have vibration on them that is being magnified by resonance or natural frequencies. One of the ways we have of identifying a resonance problem is to plot out a resonance mode shape. When structures vibrate due to resonance, they tend to vibrate.
So आप लोगों ने यहाँ पे मोड शेप देखी, किस तरह से जो है आपका स्ट्रक्चर मोड शेप से वाइब्रेट कर रहा था। वो इसने आपको बताया कि 30% जो आपका 30% जो ऑपरेटर्स होता है आपका, वो से डिस्टर्ब होता है। इसी तरह ये टैकोमा ब्रिज का जो आपके पास इंसिडेंट हुआ था, उस केस में भी यही हुआ था कि जब उन्होंने एनालिसिस किया तो उन्हें पता चला कि
Grammar can help you write quickly and confidently, so you never have to slow down at work.
और सॉरी पार्टिकल क्रिटिकल स्पीड पे हुआ था। और जब उन्होंने चेक किया तो उनके पास लॉन्गिट्यूडनल मोड से, ट्रांसलेशनल मोड से, उसके अलावा और भी जो डिफरेंट मोड शेप्स होती हैं, रोटेशनल मोड्स होते हैं, तो ज़ाहिर है इनमें से कोई ना कोई ऐसा मोड होगा जो उनके लिए क्रिटिकल होगा। तो वो एक्चुअली यही पता चलाना चाह रहे थे कि $1,000,000 स्पेंड करके कि कौन सा मोड शेप था जहाँ पे ये बिल्डिंग कोलैप्स हुई है, कि एक्साइटेशन फ्रिक्वेंसी ने जब अप्रोच किया उसकी नेचर फ्रिक्वेंसी को, तो वो जो मोड शेप है वो स्टडी करना चाह रहे थे कि ऐसा क्या उस मोड शेप में, और how we can avoid that.
An engineer is to compare loading conditions to strengths. This video is sponsored by the Great Courses Plus. More on that later. A bridge is a quintessential civil structure. Humanity's need to get from one place to another without getting wet is as old as history itself. And for so many years, there was one force with which bridge engineers had to contend: gravity. The fundamental question of bridge design was this: how can we hold up the structure itself and all the people and vehicles that may cross it against the force of gravity pulling them down?
Know the citation force.
And secondary to that, how can we do it economically for the least cost to the public, since most bridges are funded by the taxpayer? So over time, bridge designs evolved with our understanding of structural engineering and ability to create better construction materials into lighter and more efficient shapes, one of those shapes being the suspension bridge. A suspension bridge is essentially just a deck, two towers, two main cables, and connector rods which suspend the deck, hence the name. The primary advantage of suspension bridges is that they can so efficiently span long distances with only two towers, reducing the amount of material required and, more importantly, the cost. This advantage of being able to span long distances while minimizing material gives suspension bridges their iconic slender and graceful appearance. But that same lack of material reduces the rigidity and stiffness of the structure. Where before bridges were generally stiff enough that gravity was the only load that needed to be considered, now a new force started to impact their designs: the wind. In July 1940, the Tacoma Narrows Bridge opened to traffic between Tacoma, Washington and the Kitsap Peninsula. At the time, it was the third longest suspension bridge in the world. Financing construction of the bridge was a major obstacle, which led the state to pursue an innovative design. Rather than the originally proposed trusses, the bridge used two narrow plate girders to stiffen the deck, giving the bridge its iconic steel ribbon appearance across the Puget Sound. Unfortunately, that analogy extended beyond its appearance. Even during construction, it was apparent that the bridge was too flexible, even under moderate winds. Construction workers gave it the nickname Galloping Gertie. Only 4 months after it opened, the bridge collapsed in dramatic fashion. In fact, this failure was so dramatic, there's a good chance you've seen this video before. So what's happening here? You've heard of resonance, which is where a periodic force syncs up with the natural frequency of a system. The classic example is a swing. With resonance, small periodic driving forces, like pushing someone in a swing, can add up to large oscillations over time because energy is stored. In the case of wind-induced motion, the periodic driving force comes from an effect called vortex shedding.
So this is a flow-induced vibration phenomena. And by complete MS thesis on this field only. So this is how when you come in this field, then you have a multiple choices where you are going to build up your career.
This is where fluid flowing past a blunt object oscillates as vortices are formed on the backside. When these alternating zones of low pressure occur at a frequency near the natural frequency of the structure, even small amounts of wind can lead to major oscillations. This is why some chimneys are equipped with helical vanes to create turbulence and break up the vortices. The day of its failure, the Tacoma Narrows Bridge did experience resonance from vortex shedding. You can see this in the vertical undulations for which the bridge was famous. But this resonance isn't why it failed. About 45 minutes before failure, a different kind of oscillation started. You can see in the historical footage that right before failure, the bridge isn't oscillating vertically, but in a twisting or torsional motion.
So this was the twisting mode of failure. Okay? Twisting or torsional.
The reason for this change in oscillation is still debated, but one of the best suggestions has to do with the aerodynamics of the bridge. Rather than a truss through which wind can flow, the shape of the Tacoma Narrows Bridge, with the large steel plates on either side, created some strange interactions with the wind. Any small amount of twist in the bridge created vortices, or areas of low pressure, in locations that actually amplified the twisting motion. Each time the bridge returned to its natural state, its momentum twisted it in the other direction, where the wind could catch it and continue the cycle. This phenomenon is called aeroelastic flutter. It's the same reason that a strap or sheet of paper vibrates in the wind. It's a completely separate mechanism than resonance from vortex shedding.
So actually what happens, this is the, you can see this is your convection phenomena where you have a forced air coming, and then what happens when this air will pass through, then on one side there will be higher pressure of the air, on other side there will be lower pressure and will create a vacuum, and a point comes because of a pressure difference, it will create a excitation force and it will move that building structure or bridge structure.
Because the periodic forces are self-induced from the naturally unstable aerodynamic.
Now if these excitation forces that are twisting the bridge will approach a particular natural frequency that have a particular mode shape, either longitudinal mode or translational mode or torsional mode or twisting mode. Now whichever mode will be approaching, it will vibrate at a particular mode according to its natural frequency, and if it will try to vibrate at this mode for a long time, then what will happen? It will induce cracks, stresses will be generated within the structure, and a time will come when there will be a fatigue failure or a structure will collapse completely. So it is very important to understand your structures physically before solving them analytically.
Of the bridge. This flutter eventually created too much stress in the suspension cables and the bridge failed. One way that modern bridges avoid flutter is to include a gap in the center of the deck so that the pressures on either side can equalize. I cut a slot in my model and sure enough the vibrations almost completely stopped. Another option is just to make the bridge deck more aerodynamic to avoid creating vortices that push and pull on the structure. Of course, bridges aren't the only civil structures affected by the wind. Take a look at the very first practical engineering video about tune mass dampers to learn about how wind-induced motion can be mitigated in skyscrapers. For a simpler example, take a look outside at just about any high voltage power line. You might notice small devices hanging near the insulators at each pole. These are stock bridge dampers that help suppress wind-induced vibration on long cables and signs. And of course, other types of engineers contend with flutter as well. I've heard that airplanes are designed for wind loads, but I can't confirm it. These days, we have a much better understanding of the variety of loading conditions that can be faced by bridges and other structures, but much of our current understanding has come from failures of the past. The case of the Tacoma Narrows Bridge is a well-known cautionary tale that's discussed in engineering and physics classrooms across the world. The main lesson isn't necessarily that you should make sure to consider aeroelastic effects when you design a suspension bridge, even though you definitely always should, but I think more importantly, it's a reminder of how profoundly capable we are of making mistakes. When you push the envelope, you have to be vigilant because things that didn't matter before start to become important. Unanticipated challenges are a cost of innovation, and I think that's something we can all keep in mind. Thank you for watching, and let me know what you think.
सर अटेंडेंस ले ले।
ओके मैं ले लेता हूँ, आप लीव कर जाएं, लिंक आपको ड्रॉप कर दे दिया जाएगा। Actually, I am seeing, yes, it was this one. Yes, this one. It is very important to understand.
Tend to vibrate.
Please see it. This is your last video. So this was your first mode, this is your second mode. In first mode we have a 2 node and 1 antinode, and in case of second mode we have 3 nodes and 2 antinode.
Here we have a structure resonating at its second critical mode shape. you'll notice that we have 3 nodal points and 2 antinodes. Remember, with resonance, if we're going to insert a brace, we need to brace it at one of the antinodes. If we brace it at the nodal point, it has little or no effect. If we brace it at either of the...
Yes, now you can see that if they are providing a stiffness element on node, it has no effect, and if we are providing a stiffness element at the antinode point, then the whole vibration of the system mostly dampens.
Antinodes, we solve the problem.
Okay, so that's why we are always interested to find out the modes and how we can stiffen our structure and provide it more.
So it's not a matter of just making the structure stiffer, it's knowing where to put the brace.
Now check, this is your third mode, where we will have a 4 node and 3 antinodes.
This has 4 nodes and 3 antinodes. And this one is the third. Here we have the third critical node shape. Notice there are 1, 2, 3, 4 different nodes and 1, 2, 3 antinodes. Remember, if we brace at a nodal point, it doesn't do any good. If we brace at any of the antinodes, the problem goes away. Of course, my speed varied just a little bit there. So that's resonant mode.
So you people have seen that when we are providing a proper support at the antinode point, then problem goes away. So that's why we are always interested to find out the mode shapes, and it helps us to solve various resonance problems either by providing damping or stiffness elements. Okay, I hope so today lecture was very important, और जिन्होंने क्लास ली है उनको फ्यूचर में इसका बहुत फ़ायदा होगा. जस्ट किसी टॉपिक को इसलिए सॉल्व नहीं किया जाता कि उसका जो आप न्यूमेरिकल या एनालिटिकली उसको सॉल्व करके उसका पेपर में मुझे आंसर निकाल के दे दें. प्रैक्टिकल जो अंडरस्टैंडिंग होती है किसी भी स्ट्रक्चर की वो बहुत ज़रूरी होती है. सो आई हैव शोन यू मल्टीपल केसेस. फॉर एग्जांपल, यू पीपल आर गोइंग टू बी अ मैकेनिकल इंजीनियर, then we have to deal with the industrial problems, and in case of industry we have flexible and rigid rotors that are installed within the steam and gas turbines, and lot of power plants are also there. And also if you are going to be in case of aerospace problems, so aircraft fluttering phenomena is very important. If you are going to be a industrial engineer, then in case of heat exchanges, fluid elastic instability phenomena is very important. So in the same way, we people have studied the civil structures such as buildings and multiple stage buildings, and as well as bridges as well. So this is what about multiple degrees of freedom. We have covered our theoretical lecture today, inshallah, and in coming week lecture we will solve complete multiple degree of freedom topic. So do not try to miss that topic, because this will be coming week. In coming week we will solve multiple degree of freedom for a mass spring system, for a compound pendulum, for coupled pendulum, for simple pendulum, where we will have multiple pendulums, and we will solve also our torsional problems for multiple degrees of freedom. So after that we will go with the application of multiple degree of freedom in the next week. Okay, and we will solve the shock absorber. What is shock absorber? It is nothing but the application of multiple degrees of freedom. So after multiple degree of freedom topic, we will go for the shock absorber in the second week of the final. Okay, for example, this week is the first week, coming week will be the second week, and in coming week we will solve the shock absorber problems. And it is very important, they are installed in the buildings as well, and bridges. They are tuned mass absorbers का नाम सुना होगा आपने, और वो भी जो है वो आपके ट्रांसमिशन लाइंस के अक्रॉस और बिल्डिंग्स के अक्रॉस और ब्रिजेस के अक्रॉस इंस्टॉल किए जाते हैं. तो इसके अलावा ये है कि सेकंड वीक में आप जो है वो मल्टीपल डिग्री ऑफ फ्रीडम कर रहे हैं, थर्ड वीक में आप लोग शॉक अब्जॉर्बर्स को सॉल्व कर रहे हैं, फोर्थ वीक में हम जो है वो होल्जर मेथड को सॉल्व करेंगे, और वो जो है मल्टीपल नेचुरल फ्रिक्वेंसीज को फाइंड करने का एक न्यू मेथड है जो आपको करवाया जाएगा। और 5th वीक में इंशाल्लाह हम कंडीशन मॉनिटरिंग करेंगे, एंड दैट्स ऑल। दिस विल बी योर फाइनल सिलेबस। So following topics will be included in your final syllabus. For example, we will be going with the base excitation and vibration isolation. One problem will be from this topic. Multiple degrees of freedom, one topic will be from this topic. Shock absorbers, one topic will be from this, and one problem will be from the Holzer method, and one problem will be from the condition monitoring. So total 5 questions will be in the final. Yes.
सर डैम 4 में से नहीं होंगे जो सेशनल 2 का एक सवाल आया था?
उस टॉपिक को हम इंक्लूड करेंगे फाइनल में, लेकिन उसमें फिर वो हम देख लेंगे बाद में क्या करना है अवेलेबल टाइम में। अगर हम क्योंकि आपका कोऑर्डिनेट कपलिंग हम नॉर्मली करवाते थे, लेकिन इस बार हम नहीं करवा रहे, क्योंकि कोऑर्डिनेट कपलिंग जो है वो बहुत एडवांस टॉपिक है। आई थिंक सो कि अगर बाद में टाइम बचा कंडीशन मॉनिटरिंग के बाद हम वो करेंगे। तो डिपेंडिंग अपॉन द कवर टॉपिक्स, ये 5-6 टॉपिक्स जो मैंने आपको बताया ये तो लाजमन होंगे।
ओके सर।
फाइनल कब हो रहे हैं?
फाइनल जो है आपके, जो हमारे पास नोटिफिकेशन है उसमें ये है कि जो आपके फाइनल्स हैं